So I'm officially sick. I was helping a student in office hours, and they were doing multiple light coughs, like stuff like that. They weren't doing like the big deep coughs that come from within your chest, so I didn't really think much of it. But I was kind of scared. I was like, am I gonna get sick from this? And the answer to that question was yes, or someone else gave me the bug. But I really wanted to make a video because it's been like a week and I needed to update my whiteboard. So to find an excuse just to make a video that isn't just me breathing heavily into the microphone and writing on my whiteboard, I decided to make a video about geometric series, and how to make a divergent series converge in some sense. And I thought I would start with the classical example that you see in high school. I wrote everything out here because I tried to make this video earlier and I was just making a bunch of mistakes, and I think I sneezed in a video, so I didn't think people would want to hear that. So 0.9 repeating equal to 1. I saw this in high school and I didn't really believe my algebra teacher when he showed me this, but I did get what he was saying, and eventually I come around his way of thinking. So the way you do it is you start with 0.9 repeating, and I don't know what it is, so we call it S. And then we multiply both sides by 10. And what it does is it takes every digit and it moves it over by 1 to the left. So this 9 moves here, this 9 moves here. You get the idea. And there's infinitely many 9s, so you never run out. And then when you subtract the top from the bottom, you'll have S minus 10S. And then over here, the trailing 9s will disappear, and you'll end up with negative 9 on the bottom. Yes, I could have done it, this way instead, and get positives in the end, but you still end up with the same result. Except here I've written S is equal to negative 1, which makes no sense. How bad? How very bad. Plus 1. I'm still making mistakes even when I write up the script, more or less. But you end up with negative 9 over here, and you have negative 9 here, so you divide both of them off. And then you end up with S equal positive 1. Which means that positive 1 is equal to 0.9 repeating up here. Now, in general, the way this works is that you can, generalize this as a geometric series. What does geometric series mean? So we have 9 in the 10ths position, and you add it to a 9 in the 100th position, and a 9 in the 1000th position, and so on and so forth. And you can write this as a sum that's over here, where n tends from 1 to infinity. We have 10 to the negative n. And so if you replace 10 with 1 over x, or in this case, if I replace 1/10 with just x, which is what I chose to do here, I'll have ax, where a can be any fixed number you want. Here, in this case, I let it be equal to 9. But you can let it be equal to something else. If you like 8, you can replace a with 8. So you have ax plus ax squared plus ax cubed. And then a takes the role of 9, and then 1/10 takes 1 over x takes the role of 10. I'm saying this really backwards. I understand. But this is our geometric series. And the reason it's called geometric series is because this kind of has its roots in geometry problems, where if you have, kind of going off script here, but if I have a square, and let's say that the square has area 1, if I shade in a half every time, I have 1/2 here. And if I shade in this half, well, that's just half of a half, which is a quarter. And if I shade in this half, that's a half of a quarter, which is just an 1/8. And you can see the general pattern here. That's going to be a 1/16. And it keeps going on and on and on. Well, okay, don't want to do that. And you can see that as I go on and on, I end up filling in the whole square. So the idea is that this series tends toward 1, because I fill in the whole square. So the geometric part comes from the fact that, you this is a geometric argument for why it's equal to 1. Or not. I could be making that all up. I don't know the history of mathematics that well, to be honest with you. I remember when I was a math major a long time ago, I would have taken a history of math course. But as you know, I switched from math to environmental science, so I never took it. And then they told me I didn't need it. So my appreciation for the history of math is pretty lacking, despite my love of history. And then I was going to do something here, and then got screwed up, so I started over. And the idea is that this summation that we have written here has a formula. So how do we derive the formula? We can set s equal to a plus ax squared plus so on and so forth. And then you multiply both sides by x. So when you multiply both sides by x, you get ax here, ax squared, ax cubed. But then I shift everything down by 1. Okay, when I say shift by 1, I'm just pushing it over to the right, 1 position, so that the ax's are lined up, ax squareds are lined up, so on and so forth. And then I take the top and I subtract the bottom. So when I do that, I'll have s minus xs, which is here. And then over here, all these ax terms will cancel, and the only thing that's left over is this a. So everything here is equal to a. And then I have an s here and an s here, so I can factor it out and get s times 1 minus x. And then I divide both sides by 1 minus x, and I get this nice, neat little formula. S is equal to a divided by 1 minus x. But this formula only makes sense if we choose x values that are between -1 and 1. In other words, the absolute value of x has to be less than 1. And this 1 is called, in calculus words, the radius of convergence. And if you go on to take, I remember talking about it in Calc 2. So if you take Calculus 2, that's where you'll probably, learn about it. But you'll probably study it more in depth, like rigorously, in maybe a real analysis class or maybe even complex analysis. Because the reason why it's called radius of convergence is because when you, go to the complex plane, it's no longer an interval of numbers, it's a disk. So it looks like a circle of numbers that you can play around with. But there are utilities, I guess, if you want to call it that way, where this formula can make some kind of sense for x values outside the radius of convergence. So how do you get divergent series to quote-unquote converge? And the first example I've written here is, I believe, called the Grandi series. I might be pronouncing that wrong. But we have 1 minus 1 plus 1 minus 1 plus 1 minus 1, so on and so forth. And we want to know what it's equal to, so we call it s. And I notice that if I call this whole thing s and I peel off the 1 that's at the very end, I'll notice that everything that's inside here is just s times -1. I just switch the sign of all the 1s and -1s. So if I do that substitution, I'll get this 1 that goes down here. I have this minus s that goes here, and that's equal to s. And then if you add s to both sides, you'll have 1 equal to s. And if I divide both sides by 2, I get the very strange result that s is equal to 1/2. And in some ways, it kind of makes sense. In other ways, it doesn't. Because it doesn't make sense because you're oscillating back and forth between 1 and -1. But in another way, it does kind of make sense, because if you start at 1 and go down by 1, that partial sum will be 0. So if you look at the partial sums, you go back and forth between 1 and 0. And the average between 1 and 0 is 1/2. This is kind of where I think the Cesaro summation might come into play. Because Cesaro summation is, I think I mentioned earlier, a tool that a lot of people use to try and make some sense of divergent series. Okay. So another example is this result that probably you've seen on the internet, a myriad of times, is that if you add up all the positive integers, you get -1/12 somehow. And why does that make sense? Well, if you have analytic continuation, because if you're familiar with the Riemann zeta function, then you've definitely 100% seen this result before. It's zeta of -1. And the Riemann zeta function is the analytic continuation of basically this geometric series I showed earlier. Let me make sure I didn't lie. Did I just lie? What does the zeta function look like? First off, zeta of s is equal to some, it's like 1 over n raised to s, where n runs from 1 to infinity. Anyway, that's what it more or less looks like. But it's only defined for specific s's. So if you take the analytic continuation of this guy, you get the Riemann zeta function proper. And I'm definitely not going to cover that here because I know I can't do it, in this short amount of time. But I do want to show like some argument that you'll see on the internet somewhere. So just trust me, bro. I wrote that there so that way I'm covered. One thing I noticed that if I look at the previous result, if I set a equal to 1 and then I write 1 plus x in the bottom, I make the recognition that plus x is the same as minus negative x. And then it looks kind of like this formula here. So if I replace my x's with negative x, then I'll get this, alternation. So 1 minus x plus x minus x cubed, so on and so forth. And if you plug in x equal to 1, we get we get this series that we have up here. We have 1 over 1 plus 1 is 1/2. And if I plug in a 1 wherever I see an x, I get the 1 minus 1 plus 1 minus 1 plus 1 minus 1, so on and so forth. Now, a tool that's used to demonstrate this weird equality, if you want to call it that, is I take this formula that my finger is pointing at, and then I'll square both sides. So on the left side, I have 1 over 1 plus x, quantity squared, plus this big long tail of minus and pluses, and I square that. And one way that I like to think of it is I create this multiplication table where I have, one of them over here, one of them over here, and then I just start filling in the grid. I didn't fill in everything, obviously, just enough to get the idea. So 1 times 1 is 1, 1 times negative x is that, and I start to fill in the rest here. And then when I get to here, negative x times negative x, I'll get x squared. Negative x cubed by 1 is negative x cubed. X squared times negative x gives me negative x cubed. Same story here. Everything here is nice and symmetric. And then if I group by diagonals, to emphasize that's what I'm doing here, I should get a familiar looking polynomial. Well, it's not a polynomial, but I'll get something that looks familiar. So this guy up here that I'm pointing at can be rewritten as 1 minus 2x plus 3x squared minus 4x cubed plus 5x4, so on and so forth. And then if you plug in x equal 1 again, then the left-hand side, so here, if I plug in 1 here, I'll get 1 over 1 plus 1. That's 1 over 2. Square it, you get 1/4. So I get 1/4 is equal to this expression evaluated at 1. So I get this very weird divergent sum that supposedly equals 1/4. And I think there's a Wikipedia article on this that probably explains it better than me. And there's a good possibility that I didn't explain it the way that Wikipedia wants me to do it, but I don't care. It got me the result I wanted. I should be more careful if I'm a PhD student than saying that. So we're interested in this sum. We call it S because I like calling things S. And then I take it and I multiply by 4. So I have 4 plus 8 plus 12 plus 16, so on and so forth. And then a trick that they do is that they spread out the multiples of 4 down here. So I put the 4 underneath the 2. I take the 8 and put it underneath the 4. I take the 12 and put it underneath the 6 if I wrote it down. And I end up getting this. And then once I have that, I take the top and subtract the bottom so that I have 1 minus 0, so there's an unwritten 0 here, and I get a 1. 2 minus 4, that gives me minus 2. 3 minus 0 gives me 3. 4 minus 8 gives me negative 4. 5, 0 gives me 5. You get the idea. So I get this alternating 1 minus 2 plus 3 minus 4 stuff. But on the right-hand side, I have s minus 4s, and that gives me negative 3s. But we know what the left-hand side is because we just showed, quote-unquote showed, that it was equal to 1/4. So we have 1/4 is equal to negative 3s, and then if you divide both sides by negative 3, you get the very legitimate result that s is equal to negative 1/12. And that is the weird divergent series that you see on the internet all the time, if you play around with number theory at all a little bit. The only thing I'm a bit skeptical here is my multiplication table that I set up here, because when I read the arguments on it, because I had to remind myself this argument right before I've done it before, I've seen it before, but I wanted to just double check to make sure that I wouldn't stick my foot in my mouth in making this video. And they didn't really do it this way, but I thought for the purposes of this video, this seemed legit enough to write down. But if this is too inappropriate, then make sure you point that out. But everything here is about divergent series anyway. So you kind of have to like keep analytic continuation in the back of your mind when you do stuff like this. Because we are saying that 1 plus 2 plus 3 plus 4 plus 5 is equal to negative 1/12. But analytic continuation kind of keeps us honest a little bit. So look, that's the word of the day, analytic, and the other word is continuation. Read about it and correct my mistakes.